Hello, thank you for joining Vital's PLM webinar on erosion modeling using CFD. If you have any questions during this webinar, please write them in Q&A section. And at the end of the webinar, we'll go through the questions. I start with introducing myself. My name is Peyman Zahedi. I'm a mechanical engineer with experience in computational fluid dynamics in single phase and multi-phase fluid dynamic systems. I graduated with PhD in 2018 from Erosion Corrosion Research Center at the University of Tulsa in Oklahoma. During my PhD and working at Vital PLM, I had the opportunity to gain experience in different fluid physics and problems dealing with dynamic fluid body interactions, multiple fluids and interaction with solids, and erosion predictions in pipelines. So here is the agenda for this webinar. I start with an overview of the company and introduction, and then I will discuss about erosion assessment approaches, including experimental techniques, empirical correlations, or mechanistic erosion models, and also CFD or computational fluid dynamics. And then at the end, I will show a quick demo on CFD-based erosion modeling using a STAR-CCM Plus CFD package. So Vital's PLM is a solution partner of Siemens PLM products, including STAR-CCM Plus, FEMAP, and NX Nastran. Vital's PLM is based in Houston, and team consists of PhDs and masters in solid mechanics, fluid mechanics, material and corrosion, numerical analysis, and data analysis. And Vital PLM provides engineering consultancy, software, hardware, and training services. So we can help you with different safety applications, including combustion, acoustic source modeling, erosion, corrosion, fluid structure interaction, mixing and separation, chemical reaction, riser, and pipeline, vibration, heat transfer, jumper, well containment and drilling, and fluting subjects and other applications. Here I will give you a brief introduction on SimCenter STAR-CCM Plus. SimCenter STAR-CCM Plus is a multi-physics solution for safety engineers. The single integrated user interface helps you cover your complete application scope with a broad range of validated models to simulate disciplines and physics. These physics are included but not limited to CFD, electromagnetics, heat transfer, multiphase flow, particle dynamics, reaction flow, electrochemistry, aeroacoustics, and etc. You can see here some animations covering a wide range of industries and applications STAR-CCM Plus supports. As you can see, in addition to a comprehensive set of physics models, STAR-CCM Plus also enables the simulation of rigid and complex body motions with techniques including mesh morphing or overset mesh and 6 degrees of freedom motion. I also want to mention here the SimCenter STAR-CCM Plus is part of a bigger portfolio called SimCenter that combines best-in-class CAE solution, system simulation and testing solutions, as well as design, exploration, and analytics. All these solutions work together under one umbrella to help you engineer innovation into your products faster and with greater confidence. Introduction on erosion. So where does erosion happen? Erosion wear takes place when hard solid particles impact on a surface. Although erosion damage can happen due to liquid droplet impacts or cavitation, but the most common source of erosion is usually solid particles. Oil and gas produced from wells and offshore reservoirs can contain a considerable amount of sand particles. So these large quantities of sand particles in transportation systems can impact the inner walls of different fittings and equipments, such as T-junctions, valves, chokes, solder contraction and expansions, elbows, and other pipe fittings. Components in which the flow direction changes suddenly, such as T-junctions or elbows, are most vulnerable parts to solid particle erosion. So there are many different parameters interacting with each other that cause particles to impact the wall and cause erosion damage. Researchers have shown that there is an exponential relation between erosion and particle impact velocity. Also, erosion studies show that erosion rate is a function of impact angle, which varies based on material hardness. Particle properties such as size, density, hardness, and shape have also significant effects on solid particle erosion, where, for example, particle sharpness can change erosion ratio by an order of magnitude. So a sharpness factor is usually used in erosion models. And another important parameter is sand concentration in the fluid and particle-particle interaction. So erosion rate decreases as sand concentration decreases. Carrier fluid has also a large influence on erosion ratio because it can affect particles impact velocity. There's also a relation between surface hardness and erosion damage, which I will explain that in the continue. So solid particle erosion can cause severe damage and even failure of equipment. So accurate prediction of erosion and limiting the erosion to a tolerable level for continuous production can save money for oil and gas companies and avoid also hydrocarbon releases and environmental damage. Erosion caused by particle impacts is due to two main mechanisms, cutting and deformation. Cutting where is the process of displacing a piece of material by a particle which will be removed totally or partially by subsequent impacts. And deformation where is the removal of material by repeated impacts of the particles in normal direction, which results in material plastic deformation, hardening, subsurface cracking, and finally a piece of material will break off. So the total wear is usually assumed as summation of the two terms, cutting plus deformation, as you can see in this equation. As I said before, erosion rate is a function of particle impact angle, which varies for brittle or ductile material. For ductile materials, we see erosion increases with impact angle up to a maximum point, which is approximately between 20 to 30 degrees, and then it goes down to a certain value at 90 degree impact. But for brittle material, erosion increases with impact angle, and the maximum erosion is usually at normal angle. In this section, I'm going to explain some of experimental approaches for erosion measurement and assessment. This picture is showing a small scale erosion testing or direct impingement testing facility where sand particles are injected through a nozzle towards a specimen. Pressurized air that is supplied to the nozzle takes the particle from the sand feeder and inject particles toward the specimen. So experiments can be performed in different angles and velocities to determine the speed and angle dependence on erosion of the specimen. And the mass loss of a specimen is measured during the experiment, and a linear trend line is fitted through these points, which are cumulative mass loss versus sand mass throughput. The slope of this line is the steady state erosion ratio, which is dimensionless and can be plotted for all other impact angles or velocities as shown in this picture. And here, this picture is showing a large-scale erosion test in elbow geometries. This flow loop is designed and constructed at the University of Tulsa's Erosion Corrosion Research Center, and it is used for conducting erosion tests in multi-phase flow conditions. Water mixes with sand particles in this tank, and then this mixture is pumped and mixed with air before entering to the test section and this loop. And then this mixture is returned to this separator, and gas exhausts from the top of the separator, and mixture of liquid and sand is returned to this tank to recirculate through the loop. So required gas for experiments provided by these compressors, and in each experiment, thickness loss can be measured at the location of these elbows. There are mainly two measurement techniques in large-scale test facility. Electrical resistant probes or ER probes can be used in this loop to measure the mass loss during the experiment. These probes are intrusive instruments which can be used for erosion measurements in specific locations. Thickness loss in an ER probe is measured using two elements, namely reference element and sample element. The sample element is in contact with the flow, while the reference element is protected inside the probe. Therefore, the sample element experiences metal loss. As a result, its electrical resistance changes, and thickness loss of sample element can be calculated by comparing the electrical resistance between the sample and reference element. So flathead probes are usually used in elbows in order to measure the erosion rate, where the head of the probe is placed as flush with the elbow wall as possible. Thickness losses can also be measured with ultrasonic transducer technique or UT technique, which this technique utilizes high frequency sound energy for thickness measurements. These ultrasonic transducers can be installed in different locations and angles on bends. And this picture is showing data acquisition system, which is developed at ConocoPhillips. So before and after each experiment, data is gathered from ultrasonic transducers to measure the thickness loss during the experiment. This method is much more accurate in compared with ER probe approach, and the resolution of thickness loss that can be captured is in the order of 1/10 of micron, and erosion also can be measured in different angles. One useful method to study erosion pattern and determine the location of maximum erosion is paint erosion test method. These pictures are showing the sequence of paint removal in an elbow in gas sand flow conditions, where gas velocity was 31 meter per second, and pipe diameter was 4 inches. This is the location where paint starts removing. If we consider the gas velocity profile in the straight section of the pipe, it can be concluded that particles in the moving at the center have the highest velocity, and these particles are impacting this region and cause maximum erosion between 40 to 50 degrees on the bend. And then after the first impact, particles rebound and hit this region between 60 to 90 degrees on the bend, and that's why we are usually observing two eroded regions on elbows. Another erosion assessment method is using available empirical equations. Most of erosion correlations in the literature are developed in the form of this equation, which is showing that mass loss is dependent on particle impact velocity and particle impact angle and empirical constants. So this equation can be obtained by performing experiments in a small scale test method, as I explained. The next approach is CFD method. So all these experimental approaches may be very time consuming, and it may also be expensive to build experimental facilities and conduct erosion tests. Therefore, an alternative method is CFD-based erosion prediction. Erosion prediction using CFD has advantages, like it can deliver a great deal of information and also can save time and money. Erosion prediction using CFD is a three-step process. First step is flow modeling. Second step is particle tracking using a Lagrangian approach. And the last step is erosion calculation using information from particle impingements on the wall. Erosion prediction equations can be implemented into CFD software for erosion calculations, and then erosion rate is obtained in CFD as the mass of wall material removed per unit area per unit time. In low sand concentration simulations, it is assumed that the presence of solid particles does not affect the flow. Therefore, after flow solution is done, particles are released into the flow domain from the inlet to track along the pipe. If the steady flow solver is selected, the Lagrangian solver does not need to be run until the Eulerian flow solution is converged. Due to industrial importance, there have been many studies regarding solid particle erosion, which are available in the literature. These are basically available empirical erosion models in STAR-CCM Plus CFD package. The ALERT, DNV, Nelson, and OCA correlations describe impact wear from direct impact of particles on the eroded surface, and Achard correlation describe erosion due to scouring where particles impact tangentially or with very low angles. So these correlations are provided in STAR-CCM Plus, and other methods can also be added as field function in the software. So in the continue, I will looking at these correlations in more detail, and I will show some other commonly used erosion models in CFD approach. This is alert correlation, which depends on material constant, particle shape factor, and impact angle. Particle shape factor is a factor to account for the shape of the particles. Suggested values are 1 for angular particles and 0.53 for semi-rounded particles and 0.2 for fully rounded particles. Particle impact function is a polynomial function, this method, which is in terms of particle impact angle in radians. The default coefficients for the alert correlation are for liquid-borne semi-rounded sand particles eroding aluminum, but these constants and empirical values can be updated in the software according to the material of the solid body and particles. DNV correlation is also very similar to alert correlation, but angle function is different. This erosion correlation does not explicitly depend on particle diameter. However, it was derived from experimental data observed for a mean particle diameter of 225 microns. And default coefficients for DNV correlations are obtained for airborne sand eroding carbon and steel. Nelson introduced deformation and cutting wear factors and suggested that total erosion on a surface is equal to summation of erosion due to deformation and cutting mechanisms. The next correlation is OCA correlation. The strength of this model is that coefficients for a particular combination of eroded material and eroding material can be derived from more fundamental coefficients, and this model provides a more realistic correlation by including the effect of wall material hardness. This HV in the angle function is Vickers hardness of the eroded material in the unit of gigapascal. And Ashford correlation describes a mass loss to abrasion where particles impact with very low angles. For discrete element method, STAR-CCM Plus can model abrasion erosion in addition to impact erosion. And there are also other erosion models available in the literature which can be implemented as a field function in the software. For example, here we see Zhang model. In this model, impact angle function is developed based on a series of direct impact testing of Inconel 718. And the most recent semi-mechanistic erosion prediction model is Arab Najjar's model, which is developed at Erosion Corrosion Research Center at the University of Tulsa. He tested different materials in direct impingement configuration. Particle velocities were measured with particle image velocimetry or PIV. This erosion equation has been developed by assuming that erosion caused by particle impacts is due to two mechanisms of cutting and deformation. And empirical constants have been obtained by 7 different materials. This model can be added in STAR-CCM Plus by using a field function. So in the continue, I will show some validation results and comparison of experimental data with CFD-based erosion predictions using this erosion model. In the continue, I'm going to show a short demo on prediction of erosion using STAR-CCM Plus software. The erosion can be efficiently modeled using a Lagrangian multiphase model combined with an erosion model in STAR-CCM Plus. So in this demo, we are using a standard Lagrangian multiphase model for high level of solid loading, we can consider using discrete element method, which is also a Lagrangian method, or granular flow model, which is an Eulerian approach. So here I will start with creating an elbow geometry, simple elbow geometry with directed mesh. Pipe geometries are most efficiently mesh using a directed mesh operation or sweep mesh. Upstream length of the pipe is selected to be long enough to reach fully developed flow conditions. So the upstream length is 40D and downstream length is 10D. This is the outlet and pressure outlet boundary condition is considered for the outlet, and velocity inlet boundary condition is considered for the inlet. Pipe diameter is 4-inch, gas velocity is 31 meter per second, and particle size is 300 micron. So here I'm going to go on STAR-CCM software. So for those of you who are not familiar with the STAR-CCM, on the left we can see a simulation tree. So we can start with creating geometry and then defining region models and defining solvers and stopping criteria, and at the end running simulation and doing post-processing analysis and monitors different contours and plots. So here I start with creating a geometry. So I right click on 3D CAD model to open a new CAD model. So I'm going to start with creating a simple circle on ZX plane. So I right click on ZX plane, create a new sketch, and then click on creating a circle. So I'm going to make the circle the center, and then right click on the edge of the circle to define the radius dimension. Pipe diameter is 4-inch, so this radius is 2-inch. So once I'm done with the sketch, I click on OK, and then I'm going to create another sketch on YZ plane. So we can strip the first sketch on the second sketch. I'm creating the path for this sweep. So I create two simple lines and then fix this point at the center and right click on this line to apply the dimension. So upstream length is 40D or 160 inches, and downstream length is 10D. Or right click on this and apply length dimension. And then I select both these lines, right click to fillet and create a radius for this curve. So the radius ratio is 1.5. So 1.5 times pipe diameter, which is 4-inch. So this is 6-inch radius. So here I have two sketches, and now I can extrude or sweep the first sketch on the second sketch. So I go back and hold Control to select both sketches and right click and click on sweep. So we can see our geometry is created. And now I close 3D CAD model. So I have my CAD model here, and the next step is to create a new geometry part. I select the fonts. So in the parts, I have my body here, and if I click on create a new scene, geometry, you can see my geometry here, and I have my part here. Before that, I forgot to select a name for inlet and outlet. So I select the inlet surface and select a name for inlet and also for outlet, and update the part. So under parts, body, surface, I can see my inlet, outlet at default, which is other parts. I rename this part to elbow. And once I'm done with the geometry, the next step would be creating the mesh. But before that, I need to assign parts to regions because without assigning parts to regions, I would not be able to generate the mesh. So I select create one region for all parts and create a boundary for each part surface. Apply and close. So under regions, I can see my boundary conditions, inlet, outlet, and default. So my inlet is velocity inlet, and boundary condition for the outlet is pressure outlet. So I define boundary conditions here, and the next step, I can click on operations, new mesh, and directed mesh. So I select my elbow and edit on directed mesh. So we are now on directed mesh environment. For directed mesh, I need to select a source surface and target surface to create a mesh on the surface and strip align the pipe. So my source surface would be inlet, and target surface is outlet. And then the next step is to create patch a mesh on the source surface. So I'm in patch topology. So by clicking on auto populate feature edge, it creates two dots which I can displace them in preferred location. We also need two other dots on edges, on these two edges. So I click on, I select this split edges and click on each edge to create two other points. And then by doing that, I can create a patch curve and create other edges. So once I'm done here, I can modify the location of each point. So those points are on the edge. So I modify locations. I want the distance between these 2 points to be 1 inch. So this would be 0.025. And this point would be z is 0 and x is 0.4. And the same for other points. And also this one. And this one. Okay. Now I can switch from patch topology to patch mesh. So I can select like this parallel lines and select the number of divisions on each line. I select 10 for here and select other lines and divide these lines to 10 sections, and also select these 4 lines and number of divisions are 10. I can even select the distance between the first mesh to one. I select 1 millimeter distance and apply. So we can see the mesh on the inlet is created. So I need to sweep this mesh along the pipe. So I click on new volume distribution, select elbow, and in this part I can select number of layers which gonna be created along the pipe. So I'm creating 100 layers and close directed mesh, and by clicking on generate mesh, it starts creating the mesh and sweeping the mesh on the inlet along the whole geometry. So mesh is created. I click on new scene and look at the mesh here. Very structured mesh is created on the whole geometry, but maybe it's very coarse mesh and we need to refine the mesh further. I have created another file before with refined mesh. Here we can see I have very structured refined mesh, and I can continue with this refined mesh here. So the next step is to define physics models. So I start with selecting my models. This is a steady condition simulation, fluid is gas, and I select segregated flow. Gas is constant density, flow is turbulent, and I'm selecting K epsilon turbulence model for this simulation. And also I enable gravity here. So under physics, I can look at all enabled models, and even I can change my fluid here or change the density and properties of the gas. And I can also define the reference values. Gravity here is in y direction, so I change my reference value here. And also other values and initial values like pressure, which I'm going to use atmospheric pressure for this simulation, and also initial velocity conditions. So after that, I'm going to go into region and select my boundary conditions. For the inlet boundary condition, the velocity inlet in the simulation is 31 meter per second. So I change my velocity here and leave the other conditions as default. The outlet is pressure outlet with atmospheric pressure. So once I'm done with conditions, I can initialize the simulation and run the simulation. And I'm running this simulation with default solvers. And here you can see stopping criteria is 1000 iteration. So once I'm done with initialization, I can start running this simulation. But here I'm not running this simulation. I have prepared another file here with converge solution. So we can see after 1000 iteration, fully is fully converged. And I can continue with this simulation. So once we are done with full solution, here is also velocity control on a plane at the center of the geometry. So once we are done with the full solution, we can go and define other physics, which is Lagrangian phase. So I edit models and enable Lagrangian multiphase model here for injecting particles and tracking Lagrangian phase. So under physics, in Lagrangian multiphase, I need to define a new Lagrangian phase. I'm renaming this phase to SAN, and can select the models and forces acting on the Lagrangian phase. So we are injecting solid particles. So I select material particles here, which are solid particles with constant density. And I'm enabling drag force on the particles. And for other options, I'm enabling turbulent dispersion and also erosion models. So under Lagrangian phase, I can see enable models, and I can also change the drag force coefficient or use a fill function for drag force. And also we can see on the solid phase, the default material is aluminum. So I'm going to change this, the density of these particles to 2650 and change and rename the solid to sand, aluminum to sand. And then under boundary conditions, I can define the behavior of particles impacting on the wall. So under physics conditions, I can define whether particles are rebounding or escaping when impact the wall. And also here I can select my erosion correlation. As I said, there are different models available in STAR-CCM Plus. Here I'm just selecting OCA correlation. I can also define and change restitution coefficients in both normal and tangential directions. Restitution coefficients are used to predict the angle with which particles rebound off a wall. So when it is 1, it means that particles will rebound with the same angle as they impact the wall. So once I'm done here with Lagrangian phase and selecting models for Lagrangian phase, the next step is to define where particles are injected through the domain. So under injectors, I can define a new injector, select my Lagrangian phase, select part injector, and I need to define where these particles are being injected. So I'm injecting all these particles from inlet. And I can define the conditions of the these particles or number of parcels impacting per injection point. I select 50 parcel streams. Can change the mass flow rate of the particles and also define particle diameters here. I'm injecting 300 micron particles, and initial velocity of particles at the inlet are 10 meter per second. So once I'm done with selecting my injector, I just need to run the simulation for one time step. So software starts running the full solution for one iteration, and then start tracking the Lagrangian phase along the whole domain. So I have done this particle tracking, and here we can see, we can look at the erosion contour here. We can also select under tools, we can select different field functions and define preferred erosion equation or models. Here I have defined ECRC erosion model and also ECRC restitution coefficients, as you can see here, and under regions, boundaries, and on the physics models, I can see I'm using my field function for Lagrangian phase. Boundary conditions, walls. You can see I'm using field function for erosion calculations. So let me go back to presentation file. So here in this plot, we can see a comparison of predicted erosion ratio with experimental data in a 4-inch elbow. Maximum erosion ratio is plotted versus gas velocity. And we can see there's a good agreement between experiments and CFD simulations. And we can conclude CFD can provide a reliable method for predicting erosion in elbows. And these figures also showing comparison of predicted erosion pattern on elbow with paint erosion experiment with 300 micron sand size and superficial gas velocity of 31 meter per second. We see there's a V-shaped erosion pattern on the elbow since particles, as I explained, particles after the first impact or rebound and travel into preferred directions. And there are also other examples of erosion prediction using CFD in different geometries, such as casing, elbows, and other applications and geometries, certain contraction and expansions, casing, and other geometries. So for summaries, erosion assessment methods were introduced in this presentation. Erosion pattern, location of maximum erosion, and maximum erosion magnitudes are examined and validated through CFD simulations. And we can conclude CFD can be used as a useful tool for erosion prediction in pipe fittings, valve separation, contraction, and expansions. And findings suggest reasonable agreement for conditions including gas, sand, and gas dominant flows. Thank you for your attention. Let's see if there is any question. Okay, there are a couple of questions here. First question is how to define sand sharpness in erosion predictions. Yeah, as I explained in presentation, there is a sharpness factor usually in erosion correlations, like here sharpness factor, which is recommended value is 1 for very sharp particles and 0.5 for semi-rounded particles and 0.2 for rounded particles. So we need to define this sharpness factor in the equations. The next question is, can I deform a boundary based on erosion rate? Yes, you can coop the mesh morpher in STAR-CCM Plus to a boundary erosion rate value to deform the eroded boundary. So yeah, it is possible to also use deform mesh. Next question is how to estimate the overall erosion rate. We can calculate the total mass loss on or total erosion rate by writing a field function in the tools as I explained. Here under tools we can define different field functions, like here select a scalar field function and write our definition. Here, for example, I can write erosion rate times like velocity or area. So by doing that, we'll be able to define a field function to predict erosion based on dimensionless based on area, which will give us erosion rate based on kilogram per second of the sand. Okay. Okay, there is another question. How do you compare erosion prediction using this software compared to ANSYS? Yeah, it is comparable. I have done some comparison studies between STAR-CCM and ANSYS Fluent, and the basic is very similar. And also, as I compared the results I'm getting in STAR-CCM with experimental data, as I showed in presentation, we are observing very good agreement between experimental data and CFD simulation in STAR-CCM. There's another question. Any comments on steam erosion? I don't know if it means like multi-phase flow conditions. Yeah, we can model coupled multi-phase flow simulations with erosion prediction models, so we can start running the simulation with multi-phase models like BOF or Eulerian method, and then add Lagrangian phase to the flow. So we'd be able to predict erosion in multi-phase flow conditions too. There's another question. Is there any databases for material erosion coefficient for plastics? Yeah, there are some data and models available for non-metallic materials like FRP or plastics. So you need to use correct erosion model into the software for this kind of materials. So yeah, there are available models can be implemented as field function into the software to predict erosion different metallic or non-metallic materials. How are the erosion models sensitive to the mesh, especially for the boundary layers? Yeah, erosion is actually sensitive to first layer of the thickness of the first layer mesh to close to the wall. So we need to make sure our first layer thickness is fine enough to track particles all the way close to the wall. So the recommended value for the first layer thickness is usually the particle size diameter. So to make sure the particle is going all through the first layer and capture the velocity that are representing the particle impact velocity into the equations. Okay, I think it answers on almost all questions. There are also other questions. I think we are short on time right now, so we can contact you guys to answer other questions. And if you have any question, you can always contact us. And thank you again for your attention, and have a good day. Bye.